Well, welcome back to our class on algorithms and data structures. We went over a course orientation last time, and now we're going to get into the first chapter. And so we'll be talking about the data structure bags. And so this will probably be a little bit familiar now that we had the introduction, but I'll just go ahead and give you a little bit of orientation and then we'll get into it. So this is the chapter contents, in case you're following along with the textbook as well. So in here, we're going to build on the concept of encapsulations and data abstracted presented already and develop the notion of an abstract data type. So ADTs, you'll hopefully start to get familiar with that kind of a term. As you probably know, a data type such as an int or a double is a group of values and operations on those values that is defined within a specific programming language. In contrast, an abstract data type or ADT is a specification for a group of values and the operations on those values that is defined conceptually and independently of any programming language. Data structure in an implementation of an ADT, a data structure is an implementation of an ADT within a programming language. So here we're going to begin the generalization, begin to generalize the idea of grouping objects. Thus, a data structure. A collection is an ADT that groups other objects and provides various services to its quote client. In particular, a typical collection enables a client to add, remove, retrieve, and query the objects it represents. Various collections exist for different purposes. They behave on specific, specified abstractly, and can differ in purpose according to the collection. Although the collection is an abstract data type, an ADT is not necessarily a collection. To provide an example of a collection and of an abstract data type, we will specify and use the ADT bag. So that's what this chapter is about. In doing so, we will introduce a Java interface for our bag. Knowing just this interface, you will be able to use a bag in a Java program. You do not need to know how the entities in the bag are stored or how the bag operations are implemented. Indeed, your program will not depend on these specifics. As you will see, the important program characteristics is that data abstraction is all about. So let's start to get into this, but before we do, this is just a little Java review, and I'll just focus on this a little bit. What is an iterator? And so just think about it. How would you count the numbers of lines on this page? You could, if you were reading a page of text, you could use your finger to point at each line as you counted. Your finger would keep your place in the page. If you paused at a particular line, then your finger would be on a current line, and then you would be there would be a previous line and the next line. If you think of this, that page as a list of lines, you would be traversing that list as you counted the lines. So an iterator enables you to step through or traverse a collection of data just as a list, beginning with the first entry. During one complete traversal or iteration, your data item is considered once. You control the progress of iteration by repeatedly asking the iterator to give you a reference to the next entry in the collection. You can also modify the collection as you traverse it by adding, removing, or simply changing entries. So you may be familiar with iterations because you have written loops, assuming you've written programming languages in the past. And so if you, for example, if name list is a list of strings, you can write a loop for it to display the entries, to display the entire list. And I won't go into that. So the loop traverses or iterates through the entities in the list. Instead of simply displaying each entry, we could do other things to it or with it. So anyway, that's enough maybe to give you a little bit of an orientation of what an iterator is. So an iterator is an object that steps through or traverses a collection of data. The iterator keeps track of the progress during the traversal or iteration. It can tell you whether a next entry exists, and so return a reference to it. During one cycle of iteration, each data is considered once. And so the package Java util in the Java class library contains two standard interfaces, the iterator and list iterator, that specify methods appropriate for an iterator. So just keep that in mind as we're talking about this, and we will be doing iterators. So you can, for a bag, you can imagine a paper bag, a reusable cloth bag, or even a plastic bag. So it's something you would use to shop, to pack a lunch, or say eat potato chips. A bag contains things. In everyday language, a bag is a kind of container. In Java, however, a container is an object whose class extends a standard class container. Such containers are used in graphics programs. Rather than being considered a container, a bag in Java is a kind of collection. What distinguishes a bag from other collections? A bag doesn't do much more than contain its item. It doesn't order them in any particular way, nor does it prevent duplicate items. Most of the behavior could be formed by other kinds of collections. While describing the behaviors for the collection that we'll design in this chapter, we'll keep in mind that we are specifying an abstraction inspired by an actual physical bag. For example, a paper bag holds things of various dimensions and shapes in no particular order and without regard for duplicates. Our abstract bag will hold unordered and possibly duplicate items, but let's insist that these objects have the same or related data types. So you might remember before that we talked about a class responsibility collaboration card, CRC, and so here's what it would look like for a bag. So since a bag contains a finite number of objects, reporting how many objects it contains could be one of a bag's behavior. You can get the number of items currently in the bag. A related behavior detects whether a bag is empty. So we should be able to add and remove objects. So add a given object to the bag, or remove an object to a bag, remove a particular object from the bag if possible, and remove all objects from the bag. So these are the kind of things that you would be thinking about. While you hope that the bagger at the grocery store does not toss 6 cans of soup into a bag on top of your bread and eggs, our add operation does not indicate where in the bag an object should be. Remember that a bag does not order as contents. Likewise, the first of the 3 remove operations just removes any object it can. This operation is like reaching into a grab bag and pulling something out. On the other hand, the second remove operation looks for a particular item in a bag. If you find it, then you take it out. If the bag contains several equal items that satisfy your search, you remove any one of them. If you can't find the object in the bag, you can't remove it, and you just say so. Finally, the last remove operation simply empties the bag of all the objects. So anyway, that's a little bit of a perspective and orientation for the bag. So before you can implement a bag in Java, you need to describe its data and specify in detail the methods that correspond to the bag's behavior. We'll name the methods, choose their parameters, decide the return types, and write commands to fully describe their effect on the bag's data. So in UML notation, now we're specifying a class here for bag. So of course, we want to be, since we're using Java as our implementation language, to write a Java header and comments for each method, but first we express the methods in pseudocode and then in unified modeling language notation. So the first behavior on our CRC card gives rise to a method that returns a count of the current numbers of entries in the bag. The corresponding method has no parameters and returns an integer. In pseudocode, we could write this, but we'll just keep referring here to this UML description of that. Because we can detect when a bag is empty by seeing whether get current size returns 0, the operation is empty is not really needed. However, it is a so-called convenience method, and many collections provide such an operation. Okay, and these all have plus signs, and so that means that they're public. So that's something that we'll get back to in the future as we go along here. And so there's a variety of design decisions that we would be thinking to do. And so you might want to consider, we want to add a given object to a bag. We can name the method add and give it a parameter to represent the new entity. We could write this in pseudocode if this was helpful. We might be tempted to make an add a void method, but if the bag is full, for example, we cannot add a new entry to it. And then what would we do in that case? And so what should we do? What should the method add do when it cannot add an entry? And so you could think of those possibilities. You could do nothing, so we cannot add another item, so we ignore it and leave the bag unchanged. You could leave the bag unchanged, but signal the client that the addition is impossible. First option is easy, but it leaves the client wondering what happened. Of course, we could state as a precondition of add that the bag must not be already be full. Then the client has the responsibility to avoid adding a new entry to a full bag. The second option is a better one, and is not too hard to specify or implement. How can we indicate to the client whether the addition was successful? The standard Java interface collection specifies that an exception should occur if the addition was not successful. We will leave this approach for later and use another way. Displaying an error message is not a good choice, as you should let the client dictate all written output. Since the addition is either successful or not, we can simply have the method add return a Boolean value. So that's a little bit more insight into doing this. So here is the actual interface for a class of bags. So as your specifications become more detailed, they increasingly should reflect your choice of programming language. Ultimately, you can write Java headers for the bags method and organize them into a Java interface for the class that will implement the ADT. The Java interface in listing 1 here contains the method for an ADT bag and detailed comments that describes the behaviors. Recall that a class interface does not include data fields, constructors, private methods, or protected methods. For now, the items in the bag will be objects of the same class. For each, we could have a bag of strings to accommodate entries of the class type. For the bag methods, use a generic data type T for each. So those are a little bit more things. As you examine the interface, notice the decisions that were made to address the unusual situation mentioned in the previous segment. In particular, each of the method add, remove, and contains returns a value. Since our programming language is Java, notice that one of the remove methods return a reference to an entry, not the entry itself. Although writing an interface before implementing a class is certainly not required, doing so enables you to document your specification in a concise way. You can then use the code and interface as an outline for the actual class. Having an interface also provides a data type for a bag that is independent of the particular class definition. And so for the next couple of chapters, we'll develop different implementations of a class of bag. Code written with respect to an interface allows us to more easily replace one implementation of a bag with another, and that could definitely be helpful. So I won't go through the rest of the interface, but it's here that you can look it over. So let's talk about using the ADT bag. Imagine that we hire a programmer to implement the ADT bag in Java, given the interface and specification that we developed so far. We assume that these specifications are clear enough for the programmer to complete the implementation. We can use the ADT operations in a program without knowing the details of the implementation. That is, we do not need to know how the programmer implemented the bag to be able to use it. we only need to know that an ADT bag does. The section assumes that we have a Java class bag that implements the Java interface bag interface. The simple bag examples demonstrates how we can use the bag. We can notice that that once we choose the data type of the objects to be in the bag, items in this case, the data type is enclosed in brackets that follow the interface name. Also notice that the empty brackets follow the class name. All entries in the bag then must have either that data type or a subtype of that data. The compiler will enforce this restriction for us. For primitive types, you can place instances of the appropriate wrapper class into a bag. So an example would be a shopping online. And so when you shop online, your selections are saved in a shopping cart or bag until you are ready to check out. The program that implements a shopping website can use the class bag to maintain the shopping cart. After all, the order in which you choose items to purchase is not important. And so this listing shows a simple example of such a program. Here's another example. In this case, we're talking about a piggy bank. And so you might have a piggy bank, a jar, or some other receptacle to hold spare coins. The piggy bank holds the coins, but it gives them no other organization. And certainly the bank can contain duplicate coins. A piggy bank is like a bag, but it is simpler as it's the only three operations. You add a coin, you remove one, or see whether or not the bank is empty. So assuming that we have the class coin to represent coins, we can create the class piggy bank given here in this listing. So a piggy bank object stores its coins in a bag and in an instance of the class that implements the interface bag interface. The add, remove, and is empty methods of piggy bank each call the respective bag method to achieve the results. And so here is an example showing a demonstration of the class piggy bank. And so the program adds some coins to the bank and then removes all of them. Since the program doesn't not keep a record of the coins it adds to the bank, it has no control over which coins are removed, although the output indicates that the coins leave the bank in the opposite order from how they entered it. The order depends on the bag's implementation. We'll consider three implementations in the next chapters. Notice that in addition to the main method, the program defines other methods, add coin. Since main is static and calls add coin, it must be static as well. The method add coin accepts as an argument a coin object and a piggy bank object. The method then adds the coin to the bank. And so just some more of the listing, and you can look over that at your leisure. And then we also show the program output. Okay, well, let's think in terms of an ADT and we want to be using an ADT for a vending machine scenario. So imagine that you are in front of a vending machine as shown in the figure. And when you look at the front of the vending machine, you will see its interface by inserting some kind of money and press the actual or touchscreen buttons, you will be able to make a purchase. And here's some observations. You can perform only the specific tasks that your machine interface presents to you, and you must understand these tasks. That is, you must know what to do to buy a soda. You cannot access the inside of the machine because it is locked. It's a locked shell encapsulating. You can use the machine even though you do not know what happens inside. Someone replaced the machine's inner mechanism with an improved version, leaving the interface unchanged. You could still use the machine in the same way. You as a user of the vending machine are like the client of the ADT bag that you saw earlier in this chapter. The observer the observations that we just made about the user of a vending machine are similar to the following observations about a bag's client. The client can perform only the operations specific to the ADT bag. These operations are declared within a Java interface. The client must adhere to the specifications of the operations that the ADT bag provides. That is, that the programmer of the client must understand how to use these operations. The client cannot access the data within the bag without using an ADT operation. The principle of encapsulation hides the data representation within the ADT. Okay, so as we think about observations about an ADT bag, and so in the examples that we've shown, each bag is an instance of a class that implements the ADT bag. That is, each bag is an object whose behaviors are the operations of an ADT bag. You can think of each such object as being like a vending machine, as we just described. Each object encapsulates the bag's data and operation, just as a vending machine encapsulates its products and delivery system. So, and this to finish up here, since we are focusing on Java, we will be discussing those as they come into play. And so here we have the Java class library, the interface set. And this is mentioned at the end of Appendix B. The Java class library contains classes and interfaces that Java programmers use as a matter of course. From time to time, we will present members of the Java class library that are relevant to the current discussion. The Java collection framework is a subset of the library that provides us with a uniform way of representing and working with collections. Many of the classes and interfaces in the Java class library that we will note are a part of this framework, although we usually will not point out this fact. Okay, so that's going to finish up for this chapter. Thank you very much.